Alright, so welcome to Astronomy 101. This is going to be week 17. So last week, as I said, I was mentioning earlier before we started recording, I said we would get to dwarf planets today, and then when I put everything together, there's no way we have time for dwarf planets. So today we are going to be focusing on asteroids, meteorites, and comets, and the structure behind them, where they come from, some notable ones, some notable stories, and fun details there. Before we dive in, let me see if there's anything I need to tell people. So Star Trek Sunday brunch this week will happen, but Samantha's not able to make it, so it'll just be me, I think, talking Star Trek with people, which is fine too. But so if you've been keeping up with our Deep Space Nine watch, you don't need to worry about that for this week. And we're actually thinking about doing a watch party for The Wire next week before the Star Trek Sunday brunch, so keep an eye out for that. And then as well, I mentioned before we started recording, but I will not be doing Astronomy 101 next week, so we'll be taking a week off and then back the week after that. I could play some Star Trek Online on Sunday. And who knows, maybe I'll record that and put it on YouTube, and we'll see if people enjoy at recordings of me playing Star Trek Online. Who knows? All right, so let's dive in. All right, so last week we talked if anyone was going to have a holodeck addiction, yo. Okay, so we talked more about the Jovian moons last week. We had stopped on the Galilean moons, and then we went more into the Saturn's moons and Uranus and Neptune and talked about the activity like with Enceladus, and then how the rings are formed and how they carry on from there. So fun stuff. Check that out. That was from last week's. This week, as I mentioned, we're going to talk about asteroids, meteorites, and comets. So the big thing with these objects is that for the most part, they've remained fairly unchanged from the birth of our solar system. So remember, when our solar system formed, it formed out of this, nebula that was just a cloud of dust and gas, and then they all started to kind of coalesce and form planets and moons, and, went through this dynamic, turbulent time while the sun is forming at the same time. Once the star formed, once it started fusing hydrogen into helium, we had this big ball of gas that's fusing hydrogen into helium. It expelled a lot of energy. That sort of cleared out the solar system a little bit. And we were left with our planets, our moons, and various things in between. But asteroids, meteorites, and comets are all kind of what's left behind from that. So these are small objects that are those, we talked about the fact that we have those different frost lines for the different material. So rocks, metals, they coalesce, they condense much closer to the sun. Then you start to get ices condense much further out. And that's why we can look at these and see what the distribution of matter was like at the early beginning of the solar system. The number of these objects probably number in the trillions, but as we'll talk about, particularly with asteroids, they're very hard to see. So that's an important point to note as well. They're distributed all throughout our solar system. Comets, because of their high ice content, tend to be on the outside of our solar system, whereas asteroids tend to be a little bit closer to the inside, and the structure of it is fairly similar. We'll just talk about the nuances between those. And really the key is that asteroids and meteorites are pretty much the same thing. We have asteroids, which are planetesimals left over from the birth of the solar system, and then meteorites are ones that orbited the sun before they fell into Earth. So they're what we call kind of near-Earth objects that actually made contact with the Earth. We'll get into that as well. But think about it like they're pretty much the same thing. We do have some classifications for meteors and meteorites that don't necessarily distinguish them just from the beginning of the solar system, but it's pretty much the same thing. So we'll first get into what asteroids are. The term asteroids actually comes from the phrase star-like, but that's really just an appearance. This is the idea that, when they first were observed, that looked like little points. It looked like stars, but they were actually moving. But for as long as we had the telescope, for 200 years after the telescope was invented, that was how long it took us to actually see one, to notice one. And that was about 200 years ago. So it's been about 400 years since we invented the telescope. used it for science. And then right in between was when we started detecting asteroids. In that first 50 years of seeing that there's like shiny stuff that's moving in our solar system that's very tiny, it took 50 years to discover the first 10 asteroids. Now we've counted about 600,000. And the way that they're named is you name them asteroid and then the year and then alphabet, where you start with like AA and then AB and all that fun stuff. Hi, Planetary. And once they have a orbit that's been calculated, then they can be named other things after pets, friends, lovers, star, whatever. Not stars. Defeats the point. Mythology, that sort of thing. But they need to have an orbit calculated, not just, I found one. For that to actually happen. Otherwise, they just get that designation, asteroid, 2020 AZ, whatever. Yeah, there may be an asteroid, Aaron, but it's not named after me. Okay, I wish. Let's get on that. Can we community source that? But no, I don't. Nothing named after me yet. So this is a illustration model of 2 months worth of data of asteroids that are actually tracked and the orbits that are calculated in our solar system. Yikes. Yeah, this is scary and it makes you feel a little bit more nihilistic and like, just why bother looking at this? But remember, from day one, we've been drilling this home. Space is very, very, very big. It's very big. These asteroids are very, very, very tiny. So there's a vast space here, like literally vast space that we don't need to worry about it that much. And this is only a small fraction of what we suspect is out there. And the reason they're so hard to find, first of all, they're small. Once you start to get over about 1 kilometer wide, they start to coalesce into spherical shapes, and that's when they become dwarf planets. Yeah, thank you, Cairo. Not to scale. And the shapes, like I said, depend on the strength of the gravity. So if it's spherical, it qualifies as a dwarf planet, which we'll talk about in the next class. And then the shape is actually really hard to determine. The only way we can really determine what the shape of an asteroid is to get a close-up image of it. Some of you may remember when the Rosetta and Philae spacecraft went to go see the comet Churyumov-Gerasimenko. They discovered that it was way weirder shaped than they had actually planned. Thank you for the hitchhiker's quote. Peace, Demish. Yeah, no, the Philae thing was pretty awesome until you were watching the ESA storybook cartoons, and then you just ended up crying all the time. So aside from that, the key is that, so the shape is easiest to determine when you have a close-up, but they're really, really hard to see. Again, space is very, very big. On a kilometer scale, that's nothing. That's nothing. And so not only do you need that kilometer scale to be able to see that, but you also need some sort of reflection, some sort of emission, because remember, the way we see things, the way we detect stuff in space is with our eyes, with, oh, Andy, peace, damage, yay, welcome. So the way we see stuff is that it has to reflect light or it has to emit light. Now, asteroids are dark. They're fairly dark objects, so they're not going to reflect a lot of light. So there's the reflection, and then they're not emitting that much because it'll just be whatever light that they're absorbing from the sun and then re-emitting. That black body radiation we talked about when we did the radiation and physics lecture. That's not a lot. Their spectrum is tiny, tiny. So it is very, very hard to see. And yeah, a few people in the chat shouting out the Philae, Rosetta and Philae mission. It's pretty fantastic. Yeah. For me, agreed, like my peak was about 10 years earlier with, like what piqued my interest was about 10 years earlier with Cassini. That was my big thing. So much appreciate for that. So once we detect an asteroid, we're able to see it from reflecting and then emitting light. Remember, that's how we get that spectrum. It's a combination of both of those. So you have that reflection from the sunlight and then the emission, that heat that it's giving off is taking up that whole spectrum. If you remember when we did the spectroscopy stuff. So when you look at the spectrum on that asteroid, we can see that it's mostly metal and rock. It's condensed within the frost line. And then further out from the asteroid belt has more carbon-rich elements in that. And that just, again, has to do with that frost line distribution. As you got farther away from the sun, different elements started to condense out of the material as we got there. So if you're able to get a spectrum, if you can observe it, then we can get a spectrum of it. That's kind of, most of astronomy is not done just by looking at stuff and taking pictures. It's looking at stuff with those spectrographs and actually getting a spectrum off of them. In order to determine their masses and densities, you need to see their gravitational effect. So you have to see the effect that it has on another asteroid or its orbit or any of those things, particularly with the mass and size, to figure out the density. It really helps if you have like another asteroid that they're orbiting each other. You can kind of get some sense for that. So I have that Matilda example that I wrote down, and then I no longer remember what that was, so I need to look it up again, but I had it in here somewhere. Dun, dun, dun. Oh, there we go. Yep, so with Matilda, it's actually, once they did the density, once you figure out its mass and approximately how big it is, you can calculate what its density is. And they actually figured out that Matilda is only 1.5 grams per centimeter cube, which is like rubble. It's basically like a bunch of rocks and sand almost just loosely clumped together by gravity. It is not all packed as one object. So those densities can actually be really informative of stuff. Yeah, there you go. The great informant. I love it. Okay, so, oh, thank you, Cairo. Yeah, for sure. Nice resources for personal planetary protection. There you go. Yeah, I appreciate that. That's awesome. Okay, so, let me see. Going on from that, the orbits of these asteroids tend to be a little bit more elliptical, so they're not as round. Now, remember, the planets and everything aren't going around the sun in perfect circles. That's what screwed up Kepler. They're slightly elliptical, so they are not a perfect circle. But asteroid orbits tend to be slightly more elliptical and maybe, if we think about it like this, a little bit more inclined. So they're going around the sun like this as opposed to like that. So I hope that makes sense. Now, Trojan asteroids, these are actually really interesting objects. So we have, some of you might be aware, and we talked about this as we went through our solar system, you go for our terrestrial planets, and then you have an asteroid belt, which we'll come to. And then we have these objects out here that we call Trojan asteroids. And they basically hover in front of and they orbit in front of and behind Jupiter just due to the gravitational effects, how it's cleared out its orbits, how it's going around. Remember we talked about those resonance orbits? That to some extent plays into these Trojan asteroids. And there could be as many Trojan asteroids as there are actually asteroids in the asteroid belts. But these ones are out in Jupiter's orbit about once every 12 years. And you have about 60 degrees ahead and 60 degrees behind. So really, really cool objects. Again, similar to the asteroid belt, but they're a little bit darker, a little bit more carbon, and then again, they orbit out at Jupiter's orbit. So good stuff there. What was I going to comment on? Oh, P. Stemish said Kepler was a little OCD about circles. Everyone was OCD about circles. That's like back from the Greek era where they figured that like our universe is perfect and so everything must be in a circle, and they could not let that go up until Tycho Brahe, who basically viewed the world like the dumpster fire it is and was like, they're not round. And then they were like, oh, okay. And then revolution. So it's crazy how that happens. Yeah, that was basically that was Tycho Brahe's attitude. So, yes, I remember correctly too, but not nearly as many as Jupiter does. And that's primarily, so sorry, the question was, do Saturn, Uranus, and Neptune have Trojans as well? Saturn does not. I think they've all, and I think Planetary's right here. It's cold, like it's been absorbed or most likely pulled to Jupiter, and then Saturn and Uranus and Neptune have some as well, but the majority are Jupiters. And it just has to do with the mass. And again, those resonance orbits, this idea, and I'll actually show a little bit with the asteroid belt, you can see how these asteroids get distributed throughout our solar system, not just in the distance from the sun, but above and behind orbits. It kind of makes sense because you're going to have these equilibrium points where they'll happily orbit and not going to get pulled one way or the other. And that's where these like trojan areas can actually live. Yeah, physics. So the question is, does Jupiter act like a mathematical attractor, bringing in objects away from other gravity wells to orbit and impact it? A little bit of both. So there's actually some, not debate, but people have different opinions on Jupiter's role in our solar system with respect to asteroids and protecting the Earth as well. Some see Jupiter as a bodyguard, where it takes, where its gravitational pull is going to attract things to it away from Earth's orbit. Other people see it more as a bully, where it's actually slingshotting asteroids to us. It could go either way. I think it's just random chance, and I personally think that it probably saves us more than it hurts us with the amount of stuff that's out there. But, you know, our solar system is relatively settled out, so there's not a ton of impacts like that. But that's a really good question. Yeah, Stemish. Resonance plus Lagrange points. So Lagrange points are essentially gravitational equilibriums where you can lay everything out. We have our trampoline. You lay everything out and you have points that are just going to be neutral between these massive objects. And those are what we call Lagrange points. And so you can see asteroids or any object would happily orbit there without getting pulled one way or the other because they're in that perfect gravitational equilibrium. And so you can do that with Earth's orbit, you can do that with Jupiter, you can do it with anything, and they're going to be able to do that. Stemish, thank you. That's brilliant. Jupiter's presence in our solar system is chaotic neutral. I'm down with that. That's a perfect explanation for Jupiter's role. That's brilliant. And there you go. The Lagrange, ZZ top. Absolutely. Or as I said in Flight of the Conchords, ZZ top. All right. So let's talk about the asteroid belt then briefly. All right. So the asteroid belt, as I said, lays between Mars and Jupiter. Now this is what I was talking about without orbital resonance. So if you number up the asteroids, this is essentially a histogram. It's just saying how many there are by the orbital period. So remember, because we have that big bowling ball on the trampoline with the sun, that gravity well that's heading out from the sun, as part of that means that if you're closer to the sun, you orbit faster. Further away you are, you orbit slower. And so this is us moving away. This is, if you look at, Earth's orbital period, you could directly translate this, thanks to Kepler's laws, to distance from the sun. But you have Earth, Mars, and then Jupiter is out here at 12 years. And so then it broke down, okay, let's look at Jupiter's orbit and let's look at fractions, perfect fractions of it, and you see these gaps. And that's because those gaps occur where asteroids would have orbital periods that are fractions of the 12-year period, and so they get pulled one way or the other because of that resonance impact. Remember, you have that pushing and pulling where they meet at the same point every single time. So because of that, when they meet at the same point, it's going to pull them away. Earth, Mars, and Beltalowda. Yes. We love our Beltalowdas. All right. So if we talk about the Dawn mission was really cool. It got to Ceres at about 2015, and in the interim it went and observed a lot of asteroids. It got some great pictures of Vesta, and once we do the questions section, we will I can maybe pull up some more pictures of the Dawn mission because it was pretty cool. Now there's so Ceres is a dwarf planet. That's the one you see right here. This is Vesta down here, and it's sort of that one right in between there. But it actually has some really cool, there's a nice little bulge from an impact crater on the other side, which is really cool. And it's got some striation. Remember all this stuff we learned about the surface of these asteroids? So pretty awesome. And then this is just still kind of a mystery, although I saw recently they did some more analysis of the spectrographs that they were getting off of Ceres, and they realized that it does share. It does seem to be some sort of salt compounds that we have there. Okay, so that's the Dawn spacecraft, and we got that stuff. All right. So, from there, and we can come back, like I said, to cool pictures from the Dawn mission. Salty about his dad being demoted. Ceres is the grumpy teen that moved away from home, because it's the only dwarf planet, really dwarf planet, no joke, in our asteroid belt. All the rest of them are out by the Kuiper belt. So, we love it. Okay, so now let's go on to meteors and meteorites. So meteor, the term, literally means a thing in the air. That's why meteorology is like the study of the air. But what it is just that flash of light from a particle entering the atmosphere. So it's just that quick flash, the shooting star that you get, that's a meteor. Oh, peace damage, I'm coming back to that for sure. And then meteorite are the ones that make it to the ground, because they got it right, so they hit the ground. That's a way to remember that. Now the tricky thing is that meteorites, once we have them, we can analyze them, and they are actually very difficult to distinguish from Earth rocks. The way you can kind of tell is that they're a little bit darker because they burned up a lot through the atmosphere. Not enough to completely obliterate, but burned up a lot, so they got darker colored. They're very high metal, so you can actually hold up a magnet to it, and a lot of them you can attach a magnet to it. They also have high amounts of iridium, which is pretty rare here on Earth itself, but is more prominent elsewhere in our solar system. And then you can look at the ratio of the isotopes that you have there. Remember, this is decaying isotopes. So, for example, going from carbon-14 decaying down, that ratio will be a little bit different than rocks you find here on Earth. So those are all the different ways that you can analyze if something is a meteorite or if it's just a cool, shiny, metallic rock that we found here on Earth that has been here from the beginning. Meteors are not meteor. Yep. Would they be radioactive? So they don't have enough to, so they would have some radioactive materials in the sense that they would be decaying and emitting photons as they do, but not enough to actually be when we say radioactive, that sounds dangerous. They're not dangerous like that. There's just decaying isotopes that are present in meteors. And then I have to go back to Pete Stemmich's comment, which I will also drive home in 2 weeks when we talk about dwarf planets. Ceres, 100%, I wanted to be a mass relay from Mass Effect. That little shiny spot on there, I was like, oh, it's a mass relay. Mass Effect got it wrong. It wasn't sharing its Ceres, but so close. And yeah, we can't get superpowers from licking them, so sorry. And I love that comment, Storpin Base. You can't tell me what to do. You're not my real moon dad. Okay, so we have cataloged about from my old textbook that was written as probably a significant amount more than that, but we've cataloged about 30,000 meteorites. Now, having worked at a science museum, I will say that check the website before you show up to a science museum and grab someone at random and ask them if the rock you found in your backyard is a meteor. They're not going to be the ones who can answer that. You want to look at the research that's done at the local science museum, see if they accept meteorites, and we'll do an analysis on them. And a lot of them do, but randomly showing up will probably not help your cause. I speak from experience. Okay. So, meteorite falls, things that hit the Earth, can range all the way from massive craters that we've seen through, on the Earth from our past, like the Chicxulub, dinosaur-killing meteor that hit the ground, and all the way to just getting holes punched in your ceiling. And this was from Connecticut in the early 80s that a meteor fell through their ceiling, and they found multiple pieces of it while they were watching MASH. So the story goes. So, good times. So, physics asked, is it likely we've seen meteorites but not noticed that they are? I mean, it is possible, for sure. And that's why we kind of estimate those. And that's why so many people do see something like shiny, dark, metallic. They'll just take it into a museum because they can be very, very small. Yeah. So it is pretty interesting thinking that we could have some meteorites that are around that we haven't actually seen. But a lot of people track them. You know, people, that's a whole hobby to see the streak and then kind of try to trace where it goes and, you know, observe stuff like that in the sky. So it's pretty awesome. Meteorite will kill you if it hits you on the head, but that's a very, very, very unlikely, and there are no deaths confirmed to be of meteorite strike, if I remember correctly, like an actual direct impact. You have to remember too, 3/4 of our planet is covered in oceans, so they're most likely to hit those first, and then you have a very small target being your head compared to the rest of the ground. And yeah, Peace Demish, for sure. Best place to spot meteors on the ground is Antarctica. Definitely. And that's, in fact, some of the like statistical analysis that goes into how many must have hit us over time and what that distribution looks like. Because Antarctica is like so much more of a pure spot that has very little interference with it, that is a place where we can be like, okay, if it's this and the Earth is oriented like this, the issue is this with Antarctica, it's on the South Pole, and our whole solar system is kind of, you know, oriented like that. So asteroid impacts are more likely to come in from the lateral side than they are to Antarctica. But that's statistics. You just kind of take that field and say, okay, if there's this many here, the percentage likelihood is going to increase here. This is how many we're seeing. We must be off by this much. So it's pretty cool. It's pretty awesome. And yeah, dinosaurs probably have strong opinions about meteorites as well. All right. So like I said, meteorites are broken down into two categories. So let's look at this a little bit closer, right? We had asteroids. Those are rocks that are orbiting the sun that are in our solar system. We have meteors that are streaks in the sky, and then some meteorites. So all meteorites are meteors. Not all meteors are meteorites, if that makes sense. Where meteorites are the only ones that make it to the ground, but there's a whole bunch that still get burned up along the way that don't make it. So all meteorites are meteors, not all meteors are meteorites, if that makes sense. Okay. Yeah, I mean, it can do a lot of damage. If a big one, I think my friend Trevor and I did a death from space talk on meteorites or like asteroid impacts. And it had to be the size of like a Jetta. That would be a city-destroying asteroid, which is pretty cool. All right. So the two types of meteorites that we found, we categorize them into primitive meteorites and then processed meteorites. And what we're referring to with that nomenclature is essentially relative to the age of the solar system. Jetta. Jetta, thank you. So primitive means it's 4.6 billion years old. It's there, it condensed along with everything else in our solar system. You can break those into two more, where you have a stony primitive and carbon-rich primitive. Basically just means the stony ones happen closer to the sun, the carbon-rich happened a little bit further away from the sun. Then you get into the processed ones. Now they're younger by a few 100 million years, but what I'm talking about is like they might be 4.2 billion years or 4.1 billion years. They're not hugely different in that respect. But essentially what happens is the idea that they started to coalesce into something, they started to merge, they had some heat impact, right? Because when those planets and moons formed, all of that material clumping together heated up a little bit, and that changes the chemical composition of the object itself. But then it broke up, it wasn't able to, something might have hit it, shattered pieces out, all of those sort of things that would slightly change its composition. And so we can define those by the middle-rich processed. So that has a high density iron and nickel, which tend to be more the terrestrial cores. And then rocky processed have lower densities. They tend to be a little bit more like basalt. So like lava rocks. And so that's where those are coming from, these processed meteorites. Think about it as if it was like a mini terrestrial planet that then got torn apart. And then when that got torn apart, that sent all those processed materials into our solar system that eventually came through our atmosphere again and hit the surface. So, yeah, there you go. No worries, Andy. Good seeing you. And, oh, Snorfin Base. I love that era of disaster films. Was just, the science was terrible. but the disaster films were fun. So, yeah, good times. And yeah, any disasters of that are great. All right, so we have primitive and processed meteorites, and I hope those all make sense, what I'm talking about with those. They're very different compositions. It's actually fairly easy to tell the difference between those. It's basically like, did it come from something that looked like a planet and then something that was just part of those rocks at the beginning that would have formed into planets otherwise? Oh, Cairo. Earworm. No. So good. I love it. Okay. So now let's talk about comets a little bit. Comet literally means hair. Because we have these long hair-like tails. And, when you look at them, when you look at pictures of comets, like we have here, it looks like they're zooming across the sky because they have this long tail behind them. But if you stare at it, you're like, oh, that thing isn't moving relative to the time that you're actually looking at it. Now, so when I say it's stationary, I just mean like on the order of hours, as opposed to it looks like it's tearing through your sky and your atmosphere. That's an important note. And I'll hit this structure a couple times as we go through here, but essentially you have two major components of a comet. Well, three major components. You have the nucleus, that's the actual object itself. Then you have a plasma tail and a dust tail. And the plasma tail is caused by the solar wind hitting the nucleus, so whatever direction the sun is. And then you have the dust tail caused by stuff that's like sublimating off of it, and that's falling behind its motion. So that you can track, this is the direction it's moving, because this is the dust tail. This is the direction to the sun, because that's where the solar wind is blowing material off. So there's two components there, and then you have the nucleus itself. Now, I think I forgot to put in these slides, but the origin of comets is actually really interesting. Because, remember, we have our solar system, which is all pretty much in one flat plane. We have our sun, and then we have all the planets, the asteroid belt, and then the Kuiper belt, all pretty much lie in one plane. Now, I said asteroids, their orbits can be 20 or 30 degrees inclined, but that's only about like this much, right? So you have this kind of plane that's about taking up this much space. Then, beyond the Kuiper belt, we have something called the Oort cloud. The Oort cloud is a spherical shell of material, so it's completely surrounds us. It doesn't lie in this flat plane. It's much further out than the Kuiper belt, and it actually extends to almost a full light year away from the sun, so pretty much where the sun's gravitational influence stops. And that's where we've discovered most comets come from the Oort cloud. Because we have that disk, comets come in from this direction, and then they come in repeatedly, so they're orbiting. It's a closed orbit. But they're coming in from directions outside of our solar plane. They're very icy, which is why we get these, characteristics. And we know that ice is condensed much further out in our solar system, so that's how we realized comets are actually coming from the Oort cloud in our solar system, much further away. There you go, Snorpin Base. I like that. One big accretion disk with lumps in it. There you go. So our Oort cloud is really the origin of where comets come from, because they come in on these highly inclined, highly elliptical orbits. Yeah. I think that's it. I think that's everything. I mean, I've got a little bit more on comets here. So the history of them, lovely physics. So in 1577, Tycho Brahe, my man, calculated that comets were actually beyond the Earth's atmosphere. Prior to Tycho Brahe, people saw these comets up in the night sky, and they thought that they were actually objects in our own atmosphere, which frankly would scare the Jesus out of me. But he was able to calculate comets, so people had observed comets at different points on the Earth, and in 1577, let me see if it says which one it was. No, it just says used observations made from different locations. So other people had all observed the same comet around the Earth and saw it at different angles, and they realized that it had to be beyond the moon's orbit, which is pretty cool. I mean, the dude was really, really smart. He was just a dumpster fire of a human being, in the best way. But he was the first one to realize that comets were outside of the Earth's orbit. Also, hi, Book Addict. Good to have you here. And he certainly knows. Oh, I love it. All right. So after Tycho Brahe did that, It's a pronunciation thing. It's like Sharon and Karen. I say Tycho Brahe. Some people say Tycho. I learned to pronounce it Tycho, so it's embedded in my brain that way. I don't think people would yell at you if you pronounced it Tycho, so it's just one of those things. The late 17th century, that's when Newton was actually able to, from data that we had on comets, figured out that comets are orbiting the sun, that there's a regular period to some of these that come back. And then, of course, famously in 1705, Edmund Halley calculated that the orbit of a comet that we saw in 1682 predicted that it would reappear every 76 years. And there's an interesting tie, actually, and some of you Star Trek fans may have followed this when we were doing our breakdown of, oh, Lord, the two-part Star Trek TNG episode where they find Data's head with Mark Twain. Go. Whatever one that was. I have Yesterday's Enterprises embedded in my brain, and that's not it. It's the one with Time's Arrow. Thank you, Billy. Hi, Billy. See, I'm glad you're here. Comes to the rescue. Yeah, no, it was Time's Arrow. So that's the one with Mark Twain, and he makes the comment as soon as they beam him to the Enterprise, he asks about Halley's Comet. And that's actually a really good deep cut because Mark Twain believed that he had a strong connection, the person, not the character in Star Trek, had a strong connection to Halley's Comet because he was born the same year that Halley's Comet arrived. Once that prediction from Edmund Halley was proven correct, that's when he was born. And then he said, I was born with Halley's Comet and I will go out with it. And he did die like within a year of the return of the comet. So it's pretty interesting, but I like that. I like that tie as well. I know that one freaks me out as well. Ducat is in that episode. He's the one right at the beginning when Data goes in to play poker. But this isn't Star Trek. As much as we can easily turn it into. That's awesome, Shortman. I love when that happens. Okay, so here's a little bit more detail on comets. Remember I said they're highly elliptical orbits, which means they're not circular, and they're highly inclined. They come from the Oort cloud. But as they start to come in, this is the process, and it's a little bit hard to read, so I'll go through it for you. The nucleus begins to warm and sublimate. Remember, sublimate is that phase transition going directly from a solid to a gas. It doesn't melt and go into a liquid phase. It just evaporates. The solid evaporates off, and that's what we call it, sublimation. So the gas coma, this little cloud of gas, starts to form when the comet's about 5 AU from the sun. So starting to get maybe asteroid belt era. They come from the Oort cloud. Yep. And then as we get closer about where Earth's orbit is, that's where we start to get this tail forming, which is pushed out by the solar wind. So it's always, you can see here, this tail, the plasma tail, is always opposite to the sun's direction. Even though it's going in this direction, the tail isn't falling off of that. That's where the dust tail is falling out of. Oh God, thank you, Cairo. I can't even imagine. I'll pull that up later, but so this dust tail, that's from because you're getting this sublimation, this gas cloud, it's starting to break up the comet a little bit too, and so you get some pieces of dust that come off of it, but that dust is falling off like it normally would, and so it follows more the pattern of following the trail, like as if it's actually just flying through. But then we have this the solar wind, the plasma tail is always pointing away from the sun, and then it disappears and it kind of condenses. Whatever's left behind condenses back together, and then it comes back around again. And you can see this with every component, and it's actually really cool if you break it down like this. This is those size scales. Again, space, man, it's crazy. So the nucleus of a comet, on average, is about 10 kilometers. So 6 miles-ish, 5-6 miles. But then the coma, that little gas cloud that we get from it, actually extends 10 to the 6 kilometers. So that's 1, 0, 0, 0, 0, 0, 0. Yeah. That's comparison is crazy. But that's normally what we're seeing. When you see that blob that's like the main part of the comet, you're actually really seeing that gas cloud. The nucleus itself is super tiny. But that coma, that gas cloud around it is much bigger. And then we have the comet's motion is in this direction because we can see the dust tail here. And then the plasma tail, or ion tail is another phrase for it, is always pointed away from the sun. And like Cairo said, unlike a dog, a comet's always running away from the sun with its tail in front. I like that. Yeah. So here's some pretty pictures of comets. This was the one from the one that happened this summer that I can't remember the name of, that we discovered. Neowise. I got it. So this is a picture of Neowise, and you can see right here, this is the structure of it. We have a plasma tail here and the dust tail here. So from that, we can see that the sun is in this direction and the comet is moving in this direction, because we have our plasma tail going this way and the sun, or the plasma tail going this way and the dust tail going that way. And so here's sort of a little bit more of an illustration of this. Now, I would highly recommend as well, that if you're interested, look up SOHO comets, because SOHO is a solar observer telescope, and it just looked for comets that would basically obliterate themselves as they pass by the sun. And there's a lot of them, and the pictures are really cool. And so this was from 2003, watching a comet pass by the sun, but there's some, like, yeah, they're all really cool. So physics, the ion tail is blue. I'm assuming it's very hot. That's interesting. I think it's more the composition, what it's made out of. It's the fact that we have this ice that's sublimating, and then we also have, yeah, these ions that are being pulled off of it. So I wouldn't say that it's necessarily hot, but more reflecting. That's a good question. I'm convincing myself out of what I thought my default answer was for that. Let me think about that. Let's look that up once I'm done with these slides, because I think that's a really good question. Okay, let me find the detail of this. So the plasma tail consists of gas escaping the coma. Yep. Ultraviolet light from the sun ionizes the gas. The solar wind then carries it straight outwards. That's why it extends away from the sun. But there's nothing here about the temperature. I think it's just the interaction of the ultraviolet light with the gas that we're getting that causes that. What causes the two different tails, ions versus heat? Great question. So the sun's radiation is what is hitting the comet. So we have the solar wind, right? The ultraviolet light from the sun comes out, radiates, and hits the comet here. When it does, what happens is that this coma, remember if we looked at those size ratios, that's just the gas that's really surrounding that tiny nucleus. So the heat from being closer to the sun, the fact that once you get to about Earth's orbit, once you get to within the asteroid belt, essentially, you start to get a dust cloud forming around it's been a week. Let me start over. Once you get within the asteroid belt, the nucleus of the comet, which is mostly ice, starts to form a gas cloud around it that extends about so it's about 10 kilometers. This extends about 10 to the 6. So you have this huge cloud of gas that's around it. As it approaches closer to the sun, once it gets to Earth's orbit, that ultraviolet radiation from the sun starts to blow that gas away from the comet. And so that's why we get this gas tail that's always pointed opposite to the sun, because it's pushing that gas off of that coma, off of that cloud, and creating that tail. But as it's doing that, right, the comet is heating up a little bit, but it's not heating up that it's like super hot. It's just you have this ice cloud and it's getting hit by solar wind and solar radiation. That starts to break pieces off of the nucleus itself. And as those little pieces start to break off, that's what forms this dust tail. And if those pieces are sufficiently large, they aren't going to be blown in the direction of the sun. They're going to fall behind the motion of the comet, which is why they separate like this. And I think this sort of illustrates it. Was it this one? Yeah, this illustrates it pretty well. To show that as you get closer, first you just have the plasma tail here. And then you get these pieces that start breaking off, but they're breaking off in the direction of that solar wind because that's really what's happening. It's heating up and you're getting that radiation is causing these pieces to fall off. But larger ones are not affected by sunlight. That's not going to be pushing them. So as they fall off, they fall behind the comet through its motion. And then we get that dust tail that the lighter particles still get pushed by sunlight because remember, if you think of them as photons, like how solar sails work, they actually push the material. So the smaller particles get nudged a little bit by it, and then we still have this plasma tail. So there's multiple components as it goes through the process there. Cairo, yeah, that's really what I was trying to get to. So the blue is mostly from light diffusion on tiny particles, whatever those are from. So it's a good point. And then the larger particles are essentially, yeah, just reflecting light. They're going to be mostly ice anyway. So this is mostly ice dust, and that's reflecting so much light. And then this is just, yeah, ionized particles. Yeah, light diffusion. I like it. I think we came to a good answer on that. So next week, on that note, I find this hilarious, but so Ames a Doodle had a really good question here too, before people started attacking me about Pluto. So when it's in orbit further from the sun, does it replenish its material? Yes. Well, kind of. So that coma, that dust, the gas cloud around it, as it starts to move away from the sun again, it starts to condense back down. Because its gravity is still attracted to the nucleus itself. I mean, it was able to keep it on. Whatever wasn't blown off by the solar winds condenses back down, freezes back again, and then goes back. And that's really what the SOHO, was it this? No. There we go. That's what the SOHO one was studying. That's why there's so many great images of these comets, because they wanted to know how close it has to get before the thing entirely disappears, and how solid those nuclei, I guess, really are to survive passing by the sun super closely. And then, yeah, I think that works. Does that answer your question? Let me know. I hope so. So next week we'll talk about dwarf planets, the story behind them. I promise you will leave it feeling okay about Pluto, because honestly, pictures like this for me are hilarious because they're so wrong. Because Pluto's got like a billion more buddies out here. That's exactly why Pluto had to change. It's because he's hanging out with they're hanging out with all their friends in the Kuiper Belt. They have a lot of friends. That was the whole point. But anyway, or nuclei. Yeah, there you go. Okay, so with that, I'm going to stop the recording. If you're watching this after the fact on YouTube, thank you. Like and subscribe, and leave a question if you have any in the comments, and we will get to it before. And if you want to come and join us, we do this at 1 o'clock on Fridays, 1 o'clock Pacific time on Fridays on Twitch. So thank you for watching, and we will catch you next time.